Hi, this is Lab 5 Faraday's Law by Dhruv Jain. So, the introduction to this lab. The problem this week was, why does a magnet falling through a non ferrous tube fall at a different speed than a magnet falling through free space? The purpose of this lab was to conduct an experiment to collect the data for the time it took for a magnet to fall through an aluminum tube, then to create a computational model for this situation and compare the values obtained from the two. The key concepts involved in this week's lab were Lenz's law, Faraday's law, and the Biot-Savart law. They all work together to create the situation of a magnet falling through aluminum, inducing a curly electric field, which induces a current in the foil, which creates a magnetic field in the opposite direction, magnetic force in the opposite direction, and hence slowing down the fall of a magnet. The average time it took for a magnet to fall through an aluminum tube was 1.16 seconds, and the average time it took to fall through free space was 0.26 seconds. The experimental setup was very basic. I used a magnet, made sure I found out its north pole, and with its north pole facing down, north pole of the dipole facing down, I dropped it through an aluminum tube and recorded the time it took to fall through the tube. I repeated this 5 times, and the average I got was 1.16. And just to get an idea of how it compares to free space, I dropped the magnet 5 times in free space and got an average of 0.26 seconds. This is a huge difference, and this is due to the magnetic force which is created when a magnet falls through an aluminum tube. So this is the beginning of the code. These are the constants involved. So this is the one I created, mu naught, by just multiplying mu naught over 4 pi by 4 pi. This I will use later in the code. These are the measurements of the tube I used. So the length was 0.31, the width was 0.005, and the inner radius was 0.0165, and the mass was 0.023, and the mu I got from lab 3, the magnetic dipole moment, was 1.946. This is the beginning of the computational model. This involved two main functions. The first was the def dipole B. This was to calculate the magnetic field from the magnet. This is the formula I used for the magnetic field. Using this, we could calculate df dt, the deflux over time, and this is the formula for that. I created this formula by splitting the numerator and the denominator, and I used the constant mu naught I talked about earlier here. Moving on. So this is the graph I obtained using my computational model. The time in tube for a dipole, time in an aluminum tube for a dipole came out to be 0.901 for the conditions I used in my physical experiment. The average experimental value I obtained for me was 1.16. The discrepancy in these values is due to the huge scope of human error which exists when I'm physically measuring the time for each fall of the magnet. So these were the additional questions from the lab. So what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of a falling magnet change? The falling magnet would fall at a much slower rate to the one I observed. This is due to Ohm's law, as low resistivity would mean higher currents in the rings and hence a larger force acting against gravity. And what if holes or slots were cut into the tube? How would this affect the rings in the tube? That essentially means reducing the amount of foil, so hence reducing the amount of current, and going back, as the current would be reduced, the magnetic field and the magnetic force wouldn't be as strong, so the falling magnet would fall much faster, as cutting holes would reduce the number of rings exerting the magnetic force. To conclude, the experimental value yielded an average time of 1.16 seconds to fall through the tube, and the computational model predicted a time of 0.901 seconds to fall through the tube. These values are fairly close, keeping in mind the scope of human error involved in this experiment. Thank you.